Hey everybody. Today we are going to see the process of analysis 1.3. Let's start. The objective analysis of an algorithm is to find its efficiency. Efficiency is dependent on the resources that are used by the algorithm. For example, CPU utilization, time complexity, memory utilization, space complexity, disk usage, I/O, network usage, bandwidth. There are two important attributes to analyze an algorithm. They are performance, how much time or memory or disk network bandwidth is actually used when a program is run. This depends on the algorithm, machine, compiler, etc. Complexity, how do the resource requirements of a program or algorithm scale? The growth of resource requirements as a function of input. In other words, what happens to the performance of an algorithm as the size of the problem being solved gets larger and larger. For example, the time and memory requirements of an algorithm which computes the sum of 1000 numbers is larger than the algorithm which computes the sum of two numbers. Time complexity, the maximum time required by a Turing machine to execute on any input of length n. Space complexity, the amount of storage space required by an algorithm varies with the size of the problem being solved. The space complexity is normally expressed as an order of magnitude of the size of the problem. Example, big O n square means that if the size of the problem n doubles, then the working storage memory requirement will become 4 times. Determination of time complexity, the RAM model, the random access model RAM of computation, was devised by John von Neumann to study algorithms. Algorithms are studied in computer science because they are independent of machine and language. We will do all our design and analysis of algorithms based on RAM model of computation. Each simple operation plus minus equal to if call takes exactly one step. Loops and subroutine calls are not simple operations but depend upon the size of the data and the contents of a subroutine. Each memory access takes exactly one step. The complexity of algorithms using big O notation can be defined in the following way for a problem of size n. Constant time method is order 1. Big O1, the time required is constant independent of the input size. Linear time method is order n. Big O(n), the time required is proportional to the input size. If the input size doubles, then the time to run the algorithm also doubles. Quadratic time method is order n squared. Big O n square, the time required is proportional to the square of the input size. If the input size doubles, then the time required will increase by 4 times. The process of analysis of algorithm program involves analyzing each step of the algorithm. It depends on the kinds of statements used in the program. Consider the following example. Example 1, simple sequence of statements. Statement 1, 2, statement k. The total time can be found out by adding the times for all statements. Total time is equal to time statement 1 plus time statement 2 plus time statement k. It may be noted that time required by each statement will greatly vary depending on whether each statement is simple, involves only basic operations, or otherwise. Assuming that each of the above statements involve only basic operations, the time for each simple statement is constant and the total time is also constant, big O1. Example 2, if then else statements. In this example, assume the statements are simple unless noted otherwise. If then else statements. If condition, sequence of statements 1, else sequence of statements 2. In this if else statement, either sequence 1 will execute or sequence 2 will execute, depending on the Boolean condition. The worst case time in this case is the slower of the two possibilities. For example, if sequence 1 is big O n to the power uh, n square and sequence 2 is big O1, then the worst case time for the whole if and else statement would be big O n to the power n square. Example 3, for loop. For I is equal to 0, I is less than n I plus plus sequence of statements. Here the loop executes n times, so the sequence of statements also executes n times. Since we assure the time complexity of the statements are big O to the power big O1, the total time for the loop is n into big O to the power 1, which is big O n. Here the number of statements does not matter as it will increase the running time by a constant factor and the overall complexity will be same, big O n. Example 4, nested for loop. For I is equal to 0, I is less than ni plus plus. For j is equal to 0, j is less than mj plus plus. Sequence of statements. Here we observe that the outer loop executes n times. Every time the outer loop executes, the inner loop executes m times. As a result of this, statements in the inner loop execute a total of n into m times. Thus the time complexity is big O n into m. If we modify the conditional variables where the condition of the inner loop is j less than n instead of j less than m, that is the inner loop also executes n times, then the total complexity of the nested loop is big O n to the power n square. Example 4, now consider a function that calculates partial sum of an integer n. Int p sum int n int I partial underscore sum. Partial underscore sum is equal to 0 for I is equal to 1, I is less than equal to ni plus plus. Partial underscore sum is equal to partial underscore sum plus I into I. We return partial underscore sum. This function returns the sum from I is equal to 1 to n of I squared. That is p sum is equal to 1 square plus 2 square plus 3 square to the till n square, as we have to determine the running time for each statement in this program. We have to count the number of statements that are executed in this procedure. The code at line 1 and line 4 are one statement each. The for loop on line 2 are actually 2n plus 2 statements. I is equal to 1 statement colon simple assignment, hence 1 statement. I is less than equal to n. Statement is executed once for each value of I from 1 to n plus 1 till the condition becomes false. The statement is executed n plus 1 times. I plus plus is executed once for each execution of the body of the loop. This is executed n times. Thus, the sum is 1 plus n plus 1 plus n plus 1 is equal to 2n plus 3 times. In terms of big O notation defined above, this function is big O n because if we choose c is equal to 3, then we see that cn is greater than 2n plus 3. As we have already noted earlier, big O notation only provides a upper bound to the function. It is also big O n log n and big O n square. Since n square is greater than n log n is greater than 2n plus 3, however, we will choose the smallest function that describes the order of the function, and it is big O n. By looking at the definition of omega notation and theta notation, it is also clear that it is of theta n and therefore omega n2, because if we choose c is equal to 1, then we see that cn is less than 2n plus 3, hence omega n. Since 2n plus 3 is equal to big O n and 2n plus 3 is equal to omega n, it implies that 2n plus 3 is equal to theta n2. It is again uh, reiterated hence that smaller order terms and constants may be ignored while describing asymptotic notation. For example, if fn is equal to 4n plus 6 instead of fn is equal to 2n plus 3 in terms of big O, omega and theta, this does not change the order of the function. The function fn is equal to 4n plus 6 is equal to big O n by choosing c appropriately as 5, 4n plus 6 omega n by choosing c is equal to 1, and therefore 4n plus 6 is equal to theta n. The essence of this analysis is that in these asymptotic notation we can count a statement as one and should not worry about their relative execution time, which may depend on several hardware and other implementation factors, as long as it is of the order of 1, that is big O1. Exact analysis of insertion sort. Let us consider the following pseudocode to analyze the exact runtime complexity of insertion sort. Line 1 pseudocode. For j is equal to 2 to length a, do cost factor c1, number of iteration n minus 1 plus 1. Line 2 key is equal to a j c2 n minus 1, I is equal to j minus 1 c3 n minus 1, while I is greater than 0 and ai is greater than key to c4. What is this? If anybody can read this, please write in the comment section how we'll read this. Okay. And line 5, ai plus 1 is equal to ai c4 and minus 1. Okay, this please anybody tell me. Then comes 6i is equal to 1 plus 1, 1 minus 1 c5, and please tell me in the comment section. And 7ai plus I plus 1 is equal to key c6 n minus 1. So tj is the time taken to execute the statement during jth iteration. The statement at line 4 execute tj number of times. The statements at line 5 and 6 execute tj minus 1 number of times, one step less each. Line 7 will execute n minus 1 times. So total time is the sum of time taken for each line multiplied by the cost factor. So please read this equation which I've highlighted, and yeah, let's move. Three cases can emerge depending on the initial configuration of the input list. First, the case is where the list was already sorted. Second case is the case wherein the list is sorted in reverse order. And third case is the case wherein the list is in random order unsorted. The best case scenario will emerge when the list is already sorted. Worst case running time is an upper bound for running time with any input. It guarantees that irrespective of the type of input, the algorithm will not take any longer than the worst case time. Best case, it guarantees that Under any circumstances, the running time of algorithms will at least take this much time. Average case, this gives the average running time of algorithm. The running time for any given size of input will be the average number of operations over all problem instances for a given size. Best case, if the list is already sorted, then AI less than equal to key at line 4. So rest of the lines in the inner loop will not execute. Then Tn is equal to CLN plus C2n minus 1 plus C3n minus 1 plus C4n minus 1 is equal to big O(n), which indicates that the time complexity is linear. Worst case, this case arises when the list is sorted in reverse order. So the Boolean condition at line 4 will be true for execution of line 1. So step line 4 executed like this, and please read the equation, which is equal to big O into the power square. Average case, in most of the cases the list will be in some random order, that is, it neither sorted in ascending or descending order, and the time complexity will lie somewhere between the best and the worst case. The Tn best is less than Tn average is less than Tn worst. Now you can see this diagram. Figure 1.4 depicts the best, average, and worst case runtime complexities of algorithm. And yeah, okay, so here we come to the end and of check your progress too. You can solve by yourself. If you don't want to solve by yourself, then the answers will be provided soon in the description. Okay, but by the time you can try or solve yourself. And how much is left? Only one part to go, and the next lecture we will surely complete it. No, yeah, please wait a minute. It's okay. We will need 2 more videos, I guess, or 1 video. Please wait. It's more 1 video will do, okay, because we have checked your progress till 3 only, and after that we do not have. So thank you for listening, and till then keep exploring. And yeah, we completed today till here, so keep exploring.